Hey, welcome everyone to our continuation of topology. Hope you're still enjoying topology. Yeah, so today I would like to wrap up the topic about map colorings. And we already started the last topic, so the final topic for this class, which is my favorite. But of course, you should make your own calls. They're all kind of pretty beautiful. And what I will do today is I will kind of try to show you a really smart proof of the four-color theorem. Not quite, you will see. And yeah, and then we are done with map colorings. Remind you that for map colorings, we essentially had a perfect statement in the end, kind of a formula, not too difficult as a formula. It kind of spits out the maximum number of colorings, which is you need for maps on a certain surface, on a given surface, and it only depended on the Euler characteristic. I will pull it up in a second again. But for the sphere, our friend here, the world map, it gives this number of colors is 4, and indeed you only ever need 4 colors, which is kind of a fun fact of life, if you want. Okay, so let me show you the formula once more. Here is kind of the theorem, right? So whether you do it, as a reminder, whether you do it in the sphere or on R2, so you just take the sphere, get rid of the point at infinity, and just pull it open, or you do it in a disk, that's the same type of thing. And it's kind of the most basic type of question you could ask, because it's kind of the easiest surface we have. So every surface is locally made out of disks, so the easiest surface is the disk itself, right? So that's kind of what we want. And yeah, it's absolutely fantastic. And I showed you kind of the general formula, which was somewhere here, the one in red, which always works unless you have the Klein model, so ignore the Klein model. Kind of a closed formula for all colorings and all surfaces is really impressive. It's due to Heawood in kind of famous work, like well, not that long ago, actually, for mass standards in the last century. Okay, so I would like to wrap up a little bit by giving you an idea how to do this. So the point was that Heawood's formula for almost all surfaces just follows from the Euler characteristic, which is kind of really impressive. But for the sphere, we get a bound of 6 instead of the one we want, 4. So the Euler characteristic trick doesn't quite work for the sphere, which makes this theorem so difficult to prove. It has a really important, interesting history. So many people try to prove this. So I showed you the letter, the original. I still have it here. Let me just pull it up. The original letter from a long, long time ago. So it's dated back to the 23rd of October, which is almost what we have today, but 1852. And many, many people try to prove this. And they failed. There were a lot of wrong proofs published. It's kind of a theorem in math with a rich, rich, rich history. And eventually, like way later in the 70s, Appel and Haken proved this result using a machine. So this was one of the first results ever in mathematics proved by a computer, essentially. And up to date, there are only computer proofs of this theorem. So I'm clearly not going to show you any proof of this. It just would completely explode, and the only thing you can do as of today is to just do it with a computer. And it turns out to be really, really difficult. And kind of that is why this formula for Heawood is so remarkable, because as soon as you leave the sphere, it somehow gets easy, and we did the proof actually on one of those earlier slides. It wasn't so bad. But this one is just really nasty, kind of a very nice statement, but kind of really nasty and very difficult to access. So what I would like to show you, and you kind of can already tell from this one that I'm going to show you, why this one is so nasty, is kind of a weaker statement. I show you that the maximum number you need is 5. Okay, we know that the maximum number we need is 4, but the proof is beyond me. So the only thing I can do is I can show you, and it's a really cute idea of Heawood, again Heawood, how to prove the 5-color theorem, if you want. Right? So it was really, really an important breakthrough in mathematics. Let me pull up this picture. The post-stamp was released quite soon after. So it's really difficult and absolutely remarkable. It was one of, as I said, it's one of the first proofs that is completely computer. Well, most part of it is done by a computer. But this one is beautiful, so let's try to do it. Remember that I'm just showing you this because the proof is so beautiful, and I hope you agree that the proof is beautiful, but the real statement is the one at the top of the slide. I just can't prove it. That's a problem. Okay, but it's true. Okay, so how could we do this? So every map on a disk, or equivalently, any of the other spaces, can be colored with 5 colors. Okay, and we do it on a sphere, fine. Okay, and this works as follows. It essentially is the same argument as before. It's kind of really beautiful. So we argue by induction on the number of faces. So essentially, if the number of faces is very small, you can just list all maps and just do it by hand if you want. That's not very difficult. So if the number of faces is just really small, let's say it's smaller than 5. So if you only have 5 faces in total, then certainly 5 colors. So if you only have 5 maps, countries in total, then certainly 5 colors will be completely sufficient, right? So that gets us started. You could also just draw all of them, only finally many. So the really interesting one is, of course, when the number of faces is like large, like uncontrollable, and you can't really do anything by hand anymore. So how can we do this? Well, we know that the average face degree is smaller than 6, and we kind of want to use that. So this means there is a pentagon somewhere. There's a pentagonal country somewhere in our what is it, map, right? If the average degree is smaller than 6, there must be some pentagonal country somewhere, or even smaller. All right, there's some face, a pentagon or smaller. And we obviously want to use that face. So let me just do it. So essentially what we do is we have some polygon, and we know that it exists. It's some pentagon or something smaller, and you collapse it to a point, color inductively, and then blow up and see what happens. Right? So we take this face, the pentagon, collapse it to a point, and then color whatever we get, and try to see what we can do for our original map. Right? It's kind of the same idea that we had before. Right? Construct a new map by collapsing the face F to a point. Very good. And, well, we'll see what we get. So we'll just go through the proof. And that's really nice. It's kind of a really amazing idea involved. So let's see how it goes. I hope this is kind of a natural idea. You know that there exists some smallish face. So that's your only starting point. So let's start with this small face in the sense of degree of the face. There will be plenty of large faces, but we are going to completely ignore them. So we only focus on the small one. So we have no control what the neighbors are. The neighbors could be very large polygons. And we only know this little pentagon here. Good. Okay. So let's do the easy case first. Let's say there is even a square or a face of even smaller degree. I'm only doing the square. There could be a triangle or whatever, something of small degree. Good. Pick that face. The idea is always to pick the smallest face you find. Pick that face, that's my map M. Collapse it to a point, that's my map N. Okay? And find some coloring. Fine. So here I have found some coloring. Let's say it's green, blue, what is it? Red and some cream color. Okay, fine, we found some coloring. And now blow it up again. And we only need to fill the remaining face with some color. We want to prove that for 5 colors are enough, and we only see 4 colors. So there's certainly a 3/5 color that we can just put in the middle. And let's say it's purple. I hope it's purple. And let's say it's purple. Right? So I collapse the face, color inductively. Because it's a square, I only see 4 colors, at most 4 colors. So I always have my 5th free color around. And I can just plot it in the face, and I get a legal 5 coloring of my face. Doesn't make sense. I hope that makes sense. Right? And if you have a triangle, it gets even better. You only see 3 colors around. So there's clearly a 5th free color, and whatever. So in this case, we are kind of good. So somehow, the theorem is really easy if you have small countries, right? Because then you can collapse them, color inductively, and blow the countries up again. And you always have 1 free color here. Yeah? I hope that makes some sense. So in this case, I have 4 colors around. So I have my 5th free color, and my 5th color will always be purple. Because purple is fantastic. All right, so that was kind of the warm-up. Hope the strategy is clear. We're trying to do that now for the pentagon. Okay, let's assume that the smallest face we find is a pentagon. And in this business, it's always the pentagon. The pentagon is always a nasty one. So let's say we found a pentagon somewhere. We collapse it to a point, find the coloring, and see what we can do. So here's my map. Here's my collapsed map. Fine. OK, it's now, the face is now a point, and we find some coloring. Okay. And let's assume, well, let's assume that the colors I found are, let's say, only 4 of them appear. Only 4 of them appear. So they are not distinct. I have 2 faces here. So is my red red? This is red, and this is red as well, right? I could hit everything. I could hit this one. Good. Then I'm in business, because I still have a fifth free color for my face. I only see 4 colors around, so I have a fifth free one, right? So I plot it in, and it will be purple, I hope. Bash. Purple. That makes sense? I only have 4 colors around, so I have a fifth free color. I just plot it into my face. As we've only used 4 colors so far, there's a fifth free color. Same as before. Right? Okay. Well, looks like a good start. So you're really using the fact here that you have those small faces, and then the neighbors get some colors. And if you have a free color, you just plot it into your face, and you're good. Okay. That makes some sense. I hope that makes some sense. So only one case remains. And I will pull it up, in case you're wondering which one it is. The one where I have my pentagon, and I now have a coloring around where all 5 colors are present. Right now, it's all 5 colors are here. So A, B, C, D, E, or green, blue, red, creamy, and purple. Okay. Play the same game. Collapse the thing to a point. So this is already a point. We like to blow it up. Where's my picture? Whoa, don't die on me. This was too fast. Okay, so we blow it up again. Somewhere here is my little picture down here. And now we have some kind of a problem here, because all 5 colors are already present. So there is no space for putting in a 5th color, because everything else is adjacent, and everything else has already all given colors. So what can we do? OK, this is kind of a tricky case, right? I can't just put purple inside. E is already purple. Right? Or I can't put green inside, or I can't put blue inside, I can't put red inside, and I can't put creamy inside. So what can we do? And this is kind of where it gets interesting. Okay, so now I zoom out a little bit, and there will be some pattern around my little face here. So I try to find this 5th color. Right now I can't do anything. So I zoom out, and there will be some coloring pattern around, right? I just have hexagons here. Just hexagons stand for some face. And I'm interested in the colors green and red, let's say. Just out of symmetry, I just pick them. Why not? Okay, and there will be some chain of green and red faces somewhere in my map. Maybe it looks like this. Okay. Right now, I'm just saying there will be something that is around. Green and red, and they're going to touch one another, and they might be somewhere related. They might be somewhere outside. There might be some chain like this, or they might be just hanging around somewhere. We don't know. Some picture like this. So what can we do now? Right? We still want to find our 5th color, but we can't just plot it in naively. So what can we do? And now comes Hewood. Hewood is just really brilliant and says the following. OK, we essentially can do it. Let's assume our map looks like this. Well, OK, so we want to find our little 5th color. There will be some green, and I'm ignoring all other regions. I only display the green and red regions. There will be somewhere along the face. And now Hewood says the following. Well, if we are back to this case, then we are good. Remember, we had this case where only 4 colors were present, and we had space for the 5th color. So maybe we can somehow go back to that case. If we're in this situation, we're good. There's a 5th color. We just stack it into the face. Okay, and now Hewood says the following. It's pretty brilliant. Okay, we have this local picture. Fine. So why not recolor green and red along? Just change the green and red coloring. So let's make this face red. Okay, if you make this face red, then you have touching red faces. So you need to make this face green. And then you have touching green faces, so you make this one red. You make this one green, you make this one red, and so on. So you just swap colors along this chain. Let me do that. Okay, so I swap colors along the chain. and everything else is fine, right? Those colors just swap places, and my little picture down here is fine. And now I can fill in green in this case, right? Okay, so if I have all colors present, I pick kind of two that are distant, I follow the chain of colors, and I swap along that chain, and I get a picture where one of the colors is swapped because I swapped them. And locally, I can just now fill in my little friend green. Do I do this? Come on, don't die on me here. Oh, I don't. Oh, I do. Very good. So locally, you can now fill in green, right? So what did we do? Okay, we follow some chain of colors, swap colors, and locally the picture is fine again. So that's what he would say. So this is pretty brilliant. Just swap colors. Just follow the chain of colors. Just swap all of them, and the property of adjacent faces having different colors will stay the same because you just swapped two colors. Yeah? So you can actually do that. Hope that makes some sense. So I just swapped green and green and red, and I have now two red and no green, so I can put in green in my missing face, and I'm good. I have my 5 colors. Does it make some sense? It's kind of brilliant, right? You just swap colors along a chain. Okay, almost there. Now he would says, okay, there's one stupid case. My chain could go all the way around, and the chain from green touches actually red. So swapping colors wouldn't do anything because they just would swap on the face itself. Right? So the chain goes around, blah, blah, blah. So swapping colors along this chain, this one here, doesn't do anything because our little picture would just have now, let me try to draw it, would now just have green and, we have, let's say, yellow, and I clearly have some purple somewhere, would just have green and red swapped. So we are still stuck in the same situation as before. Right? Just we swap colors. Okay, so it looks like the proof can't work. So what do we do if we're in this case? So the faces go around like this and kind of nicely block the color swap. So if you swap colors here, not much will happen. It doesn't get us out of our misery. We are still inside of a problem. Okay, so what can we do? And now he will says, and now comes again a brilliant trick. Well, it doesn't really matter. So let's still swap colors, but maybe let's do it for, let's see, for B and E. Why do I want B and E? Well, the idea is now, okay, the chain of colors goes all the way around from A to C, so swapping doesn't help. But as you can already see, I can't have a chain of colors going now from B to E with the corresponding colors blue and purple, because my original chain is blocking it. So these guys are now good, and you can just swap colors for them. Right? So if you are blocked, the blocking string, the blocking path actually will block another one. It's kind of an interesting observation. So you're back to the original setting. So B and E cannot be connected, right? So we can just swap colors for B and E in this situation. I could have used D and B, for example, as well. Just one of the others. Oh, so just swap colors. And let's say make the blue one purple and just swap colors again. And we're good. Then we have a free face down here, a free color that we can fill in. In this case, blue. So we just plot it in and we're good. Bash. Well, come on. I didn't plot it in. Oh, that's really bad. So let me do it. For some reason, I decided not to do it. So this one gets the color blue. And we're done. These are all cases. If you just sit down for a while and think about it, these are all cases. So we are done. So what have we done? So that's the proof. That's kind of an interesting thing. It clearly uses that we are in the plane because we are using this chain that goes around and then blocks another chain. So it's kind of an interesting. And then now if you think about doing the same argument on a more complicated surface, this argument doesn't work, and that's why the coloring number goes up, actually. Right? So here's the difference between the plane and anything else. So let's run the proof once more because it's kind of really nice. Hopefully it wasn't too complicated. I have just too many slides. Whoa, don't die on me. And they're loading a long time because they're very large. Okay, so this was the easy case. Whenever they are only 4 colors around my face, I can always find the fifth free one and just plot it in. I hope that one was reasonably clear. So whenever there are only 4 colors around, plot in the fifth one, and we're good. Okay. And then what's this funny case where we have all 5 colors around? We kind of need to deal with this case, and we essentially swap colors. And the point was you always find a pair of colors that you could swap. And then you're good. Then you're back to the original setting here. So in this case, you swap colors green and red. You're back to the 4 color setting, and you just plot in the remaining color. So let's plot in the remaining color. And we're good. And that's essentially the proof. Right? So you contract the face and find an appropriate coloring. But you can already see why the 4 color theorem gets now a bit tricky. Because if my biggest face is a pentagon, then I really need to work very hard to get only 3 colors around so I can feed in my 4th color. And essentially, the computer proof is going through a lot of cases like this for the 4 color theorem. There are just zillions of them, and there's just no hope to do that by hand. So that's essentially the difference. But the proof itself looks very similar. You take the pentagon, the worst case, and you try to find the coloring around it with only 3 colors so it could fit in the 4th color. Or in this case, with 4 colors, so it could fit in the 5th color. Okay. Where's my end of my proof? This completes the proof. Bless you. This completes the proof of the 5 color theorem. And I just wanted to do this because I think it's actually a nice proof. I will not ask about proofs in any exams or anything. But I think it's pretty cool. It's kind of a nice idea, and it works out. It's kind of really interesting. And you can really tell that this is happening in the plane, right? Because we use this chain, and you recolor faces. Pretty nice. Cool. OK, let me summarize, because halfway into this lecture, we're going to the final topic. So let me summarize this, what we have seen here. Hoping to try to go back, but I probably have too many slides anyway. Come on. It's a very large file. Okay, blah, 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 blah. Okay. So this is essentially the main theorem. So let me pull up the map again. Let me pull up some more examples. Right, so the original question, how many colors do you need? Really difficult to answer. I showed you the 5 color version, which is slightly worse. Right? You need 5 colors. But for all real world maps, you can always find a sufficient coloring. And finding a coloring is somewhat difficult, so I'm not going to tell you how to do that. But just the statement itself, that there's always some 4 coloring of your map, is pretty beautiful. So if you're ever stuck, as I said, coloring counties in England, which was the original question of my little letter, you only need 4 colors. So it's definitely sufficient to take 4 colors with you to the exam. Is it right? Probably it is. Anyway, and then we discussed a little bit the generalization of this theorem, and we ended up with coloring surfaces on coloring maps on other surfaces, and there's a closed formula that does the job. It's kind of really remarkable, right? Say it again. I know I sound like a broken record, but if you just know the history of the story, and the SWE is so difficult, and then someone pops out just out of the blue, that pops out a formula for all surfaces, this is just extremely remarkable, actually. So I hope you kind of want, but the formula is not so bad, right? It's not super easy, but it's also not difficult. There's some square root involved that came from studying the roots of polynomials. Cool. So let's hope my slides survive going backwards. Oh, come on. Very good. And I showed you this proof, which hopefully was enjoyable. Come on. These pictures are really large. That's why it takes so long to load. Come on. Fine. Awesome. OK, so this topic was kind of part of surfaces and graphs. And this whole class is about 3 topics. So we somehow need to go to the last topic, which is my favorite, and maybe your favorite as well. We'll see. And it's kind of a little bit of a pity because it's the last topic. So people usually don't like it because it's the last topic, and I've already thrown so many topics at you. But it's really cute, and I hope you will enjoy it. And definitely, like, the exam will be split exactly in 3 parts, asking about graphs, surfaces, and whatever kind of object comes up next. But that's just what it is. The last topic always has a disadvantage compared to all other topics somehow. Towards the end of the semester, people get tired. That's totally fine. Anyway, I hope you will enjoy it and have videos for you that we can watch and all that fun stuff. So hopefully it will be a nice ride. So for the remainder of this lecture, which is like 4.5 more lectures, we will go and study knots. Okay, and what is a knot? And a knot is an absolutely fantastic idea. It's a field of mathematics. It's called knot theory. And it's like, it just came out of nowhere. People just studied it for fun. But it turns out to be one of the most applicable fields of all of mathematics. It's kind of really, really beautiful. It's kind of a mixture between, well, topology and kind of real-world applications. I will show you a knot in a second. Obviously, a definition is empty without a picture. OK, so this is a definition, but let me pull up some examples. Oh, that was too fast. So a knot is just, you take a string, take it in your hand, and you put the ends together. But you can bend the string in any way you want. I have an animation for you in a second. And you get those pictures. And the one you want to remember is the unknot. This is this guy. This is kind of a boring knot. It's just no knot at all. Okay. Formally, it's just an embedding of S1 into R3. And this is now a 3-dimensional picture, and I only show you like a 2-dimensional projection of it. I will make that more clear in a second. But these are the kind of objects we would like to study, and they're different from what we have done before, right? So don't compare them to, this is a new topic. Don't compare them to surfaces or graphs. They're different type of objects. All right, let me show you a little video. Boop, boop, boop. Come on. Ah, there you go. So a knot is really, you take a string, you can really take a real-world string, and you put it together in some way. And you really need to put the ends together, because otherwise you can take it apart. We're doing topology, we can bend it any way you want. But if you put the ends together, like this, then, well, this is a knot. And this is not trivial. Some knotting, it's some knotting of something, as you guys could already see. And we study those things up to deformation. So really just take it in your hand as a string, and just if you move it around, it moves around. And it's still the same type of object. Okay. And we're allowed to do any bending on knots that we want to do. Like moving it around is no problem at all. The only thing we are not allowed to do is to cut it, because if you cut the knot, you could take it apart again. But otherwise, all operations are fine. So if I cut it, you could just take it apart. Okay. So it's really a real-world knot, but you'd stick the ends together, because mathematically you could just undo it otherwise, as you can see. If the ends are not together, you can always undo every knot. And you know that yourself, because if you have ever a knot, I'll show you a knot in a second. In real life, you can somehow always undo it. It's a bit of a pain and annoying, but you can always undo it. Okay. Let's run the picture a little bit more. It's really like the ends are fixed. Right? You're not allowed to move them, and it's this picture of a knot inside, and we really only move those. So whether you just put them together, you should think of them as holding it in your hand. You're not allowed to move the ends, and then it really is a knotted object. You can still bend it around, but anyway. Okay. And they really come up everywhere. So it's kind of an interesting thing. So my shoelaces are knots, for example, where the ends are not together, so I can undo them. That's why I can undo them. And we're trying to understand those objects. So it's kind of a lot of fun. They come up in computer chip design, which is a lot of fun. In biology, I'll show you some pictures from biology in a second. And we're trying to understand. I will put up the main question at the end of the lecture. But this is kind of what we are trying to do. So here, they come up in biology. So it turns out that DNA, so there's the pictures of DNA, and what you read below is the mass name for the knot you see. So the 3-1 is this guy here. So, and the other ones, we will see them anyway. So DNA likes to form knots. So maybe you can actually see that this one here was the one from my video. Kind of looks like it. So the DNA forms knots, and it turns out that most of the properties of DNA are encoded in how it knots itself. And similar for proteins, proteins form knots, and most of the properties of proteins are really encoded in how they sit in space. And that's exactly what we want to study, how those things sit in space. So this is inside of our bodies. Kind of a really nice picture. And it turns out that they really form the knots we will see in this lecture. Like the 3-1 was the one from the video. And you can use the tools we study in this lecture to study those DNA knots. So and people really do that in the real world, similar for proteins and many, many, many other things. It's kind of very interesting. And it really came up really late, so that really only got started in the 1980s. So that's like super new for mathematics if you think about number theory or geometry, which started with like 4,000 years ago or something. So it's really, really an interesting field of mathematics. Here's another knot. I took this photo, so this is usually how you see knots. Again, this is not a knot where you have ends put together because you can't take it apart, right? So if you really, so if you're looking at my desk, you will find something like this. So we're really studying some knotting in life. So this is a knot. Here's some more knots. So this one is the most trivial knot. So everything is something trivial. Everything has some trivial object, and this is called the unknot. It's kind of the trivial thing, and knots get very complicated, as you can see in this picture already. Okay. And the main question we would like to study is the following. When is the knot the unknot? And I remind you again, the unknot is kind of the one boring picture you have, the circle itself, so without any knotting at all. And you kind of would like to tell that from the knot. So this is the unknot. This is also the unknot. It just is a little bit strangely projected. I will tell you in a second what that means. But if you just undo this little twist up here, right, it looks like an 8, but you can just untwist it, and it's just really the unknot itself. These two are equal. This one is also the unknot. I just put in another twist. So all of these are equal. We somehow need, exactly like for the surfaces, we somehow need the machinery that tells us whether a picture represents a certain type of knot or not. So all of these are trivial. All of these are unknots. And this one is much more delicate. It actually loads much longer. This is also a picture of the unknot, and I'm not expecting you to see that. It's kind of the whole point of the game is that there are very difficult pictures of knots. So you can undo this knot. If you really would build this out of rope or something, you could undo it. But just by looking at it, it seems to be essentially like impossible to tell it apart, right? So this one is actually an unknot. It just sits there in space. But it sits so weirdly in space that you really can't. It's really like my picture from before. So this one, if you just do it on your desk, this one is also an unknot, and we all know that because you can take it apart if you have some time. But it's not so obvious from the picture itself. And here we are facing the same problem. We have an unknot here, but it's not obvious what to do. So what we need is exactly at the same stage where we were with surfaces at the very beginning. We kind of need some tools to distinguish knots. So let me run a few more knotty videos for you. So here's a knot, one of the more complicated ones. Yeah, very good. And it sits somewhere in space. That's how I would like you to think about those knots. Very good. And what we will do, or what I always showed you, is a projection of a knot. It's really this idea that I can only show you a two-dimensional picture. So instead of showing you the knot itself, I will show you the shadow of the knot. And that's exactly what we draw. I go back to the slides in a second. This one is called a knot diagram. And the only additional information we will remember is which strand goes over and under. And that's why it's called a knot diagram. So this is a diagrammatic presentation of the same thing. I hope that's reasonably clear, but I can draw it in two space. So it's a projection of the knot into two space. I hope that makes some sense. So let's go back to the slides. So actually, what I'm saying is that this guy is the unknot. So if you have it in your hands, yeah, then it is just a line. But if the other ones are also unknots, so if you have them in your hands as a piece of string, it's really just a circle. But the projection is kind of shitty. And I kind of projected it in a weird way, so the projection looks a bit strange. And that's why it's not obvious. Well, I mean, for the first picture, maybe it is, but eventually you can have really, really complicated projections, like the one down here. And it's really difficult to tell just from the projection whether this is a knot or not. It's the same problem we faced with the surfaces. The polygon decomposition is a two-dimensional picture just projected on the plane of a surface, and we kind of need some way to tell which surface it is. It's very powerful to use it because we can just do it on a piece of paper or on a computer screen. But somehow to tell the knot apart is, the surface from the polygon was the whole point of the surface part of the lecture. So the whole point of this last part of the lecture is to try to tell what knot it is by just looking at the projection of the knot. I hope that makes some sense. Okay, let's have another video. So here's again some knot. Plop. And the question we are trying to study is, so this is actually, well, let's do it again. So this is actually a slightly complicated projection of a quite easy knot. So let's do it again. It was a bit too fast. Right? You can see this little move here. So this strand is actually in front, and the other one is in the back. So you can just pull it away. You can pull this one away. And it turns out that the knot is easier than it looked like from the beginning. So oh, it actually does it again. Okay. And we are trying to study all those little properties of the knot. So here, you can see that downstairs. You can just pull it away. Right? There's one move like this. You can undo kinks. This is a move like this. And you can just straighten out things like this. And these moves are called the Reiter-Master moves, and they're enough to determine the knot from the knot projection. Okay, so they're called the Reiter-Master moves. So we'll have them like all the time. There are only 3 of them. So there are only for surfaces we had 2. It was the surgery moves, and now we have 3. And you can always do them on the knot. So here you can see, for example, the Reiter-Master 3 move is just you pull a string on top or below another string. This one is kind of a little bit easier. It's just crossing your arms and just undoing it. Just pull them away, and you can somehow simplify the knot. Here's another one. So here, you can also do it the other way around. You can kink something in. So you can always massage the projection. What you see now is a projection. I hope that's reasonably clear. Okay. And it turns out that those 3 moves are completely enough, and we only need to ever study those 3 moves. In a paper from the 20s by a mathematician called Reiter-Meister. Okay. Let's do 2 braids right now. Okay. So we are trying to study those. I have one more video for you. So let's just run it as well. Here's a knot again. Very good. Here's another knot. Very good. And the question is essentially, are they the same, right? So is there any type of move that makes them the same, or is there any way of making them trivial, for example? They don't look like it, so if you really just build it out of rope, it's kind of easy to see that they are not, but we want to have some tools to do this. So let's do another one. There you go. That was the one from before. Here's another one. And they are actually the same, right? So are they the same? Good question. We need some tools to decide whether they are the same or not. Okay. And in this case, they are. Let's just do it, or let's the video do it, because the blue string is in the back, the red string is in the front, so you can just kind of undo them. And this one is just kind of a little kink that does really nothing. You can just undo it. And if you straighten it out a little bit, already looks like the one from below. So you just need to straighten it out. One more move. And then you can get rid of the kink. Final little kink here. And it's actually the same knot. Okay. So this is what we want to do. So we'll study those. Let me pull up the projection again. We study these knots by looking at an easier picture, namely by, so this was my little knot here, sorry, by looking at the projection it forms on just taking a light source, project it down, and whatever comes out is called a knot diagram, and we kind of study knot diagrams, and we want to tell the knot from its diagram. It's kind of really the same as for the surfaces. We wanted to know what surface we have from a polygon decomposition, and now the players have changed. We have a knot and a knot diagram. Good, so let's do that again. So what we want to study are those little things. A knot is nothing else than you take a piece of string, you put it in free space in some way or form. I hope I've showed you enough examples of knots that they can kind of get really difficult, and you bend the ends together. Oh yeah, that's a three-dimensional picture, and the best way of doing this is just taking it in your hand. But the way we study it, because I only have two-dimensional slides, is we look at projections. So everything you see here is a projection of a certain knot. And the question we are trying to address is when two knots represent, when two projections represent the same knot. So here, for example, this is kind of a really tricky one. So let me get rid of this one here. Okay, so you can have this knot which goes over, under, like this. Or you do it under, over, under. So you're really just swapping over and under, like this. Let me go rid of the drawings. And you can ask the question, if you do this, actually, are they the same? Right? One of them goes over, under, following the string. The other one goes under, over. Are they the same? Can you turn your head, or can you turn the knot to make them the same? Doesn't seem to be completely trivial. And is the final knot here on the right-hand side, is it the same as any of the others? Are those trivial? That's essentially the type of questions we would like to answer. So keep in mind that knots can get really complicated. Yeah? So like this knotty picture of life itself, if you want. And the question is, even if they look very complicated, maybe you can undo them, maybe they're actually simpler than they are, and what we really need are, the model knots, are really some more tools to study them. And that's exactly what we are going to do in the remaining part of the lecture. But I think this is a good point to stop. So thank you very much for coming today.